To this DS talk, I think it's about time to start. So today's speaker is Benjamin Rodriguez, who recently started as a DS staff, as assistant professor at the Institute of Mathematics and Computer Science. Ben is an expert in lattice field theory, or the study of strong force using numerical simulations. He's an expert in high-performance computing and again numerical simulations in general. And in this talk today, from quarks to which are the smallest components of the universe to the whole universe, so it's quite broad subject. I hope it will be exciting, and we'll look forward to hear from you.
Thank you very much, Claudio. Thank you all for showing up, and thanks for the attention already. My talk will take you on a journey from the smallest building blocks, as Claudio just mentioned, which are quarks, and to the whole universe, and basically starting to how to map out the whole thing. And I will cover two important ingredients in my everyday's research, which is computer simulations. So I explain how we do our computer simulations to study the strong force, which is one of four fundamental forces in nature. And I will explain all four in the following slides. So as I mentioned, we start with the smallest building blocks. So the smallest building blocks are quarks, which we just illustrated here. They come in various different flavors and shapes, but I will come to that later. These form then protons, neutrons, the inner part of an atom. And then, of course, many atoms form, for instance here, sand, or the atoms of a sand grain, which then, of course, is in a very vast majority on Earth. And then we go bigger and bigger by scale, and Earth is only just one planet in the solar system, which just is one solar system in the whole galaxy. And of course, the whole observable universe is made up of many, many galaxies. And what I'll try to talk about is basically how the strong force, one of the four forces in nature, governs it all. So basically, we'll have an impact from the smallest part. So basically, how quarks, which are a particle of the strong force, is made up. Everything which we can see around us. So, as mentioned, basically, as we considered how atoms look like, or basically as people will like try to draw a cartoon, because the real life actually is quite different. There's an outer hull given by the electrons, which circle around the nucleus, and the nucleus itself is made out of protons and neutrons, and these itself are made out of three quarks, which is currently the smallest particle we know is, and we consider basically these two to be the building blocks, because these are the rudimentary particles that form every atom, every nucleus, and everything around us. And this is basically a manifestation of one of the four forces. As I mentioned, I will cover the strong force, and here is again showing a proton made out of three different quarks. But of course, we know there's more than one force. So we have so far the understanding that there's four forces in nature govern us, and these basically explain all the interactions and all the constitutions. The most probably familiar one is gravity, because we feel the influence every day. We pull to the ground, and also it explains like how big galaxies form and how are they stable and how they rotate and everything associated to that. Electromagnetism is also quite common to us, because all the electric interaction, like in smartphones, also lightning as weather, and also like every phenomenon that is also evolved into light is governed by electromagnetism. Then there's two additional forces, which are the nuclear forces, and there's the strong force and the weak force. As physicists are typically not very creative on naming. The strong force indicates that it is supposed to be very strong, where the weak force is a much weaker force, and I will come to that later on. But the weak force is one particular example. That is a force that actually doesn't bind anything together. It actually only destroys things by why I showed here the cartoon of a radioactive decay, which is explaining how a neutron decays into a proton and an electron antineutrino. And this is something the weak force is responsible for. So let's go through them one by one and talk a bit what the matter particles are that are influenced by it, starting with gravity. So it couples to mass. It's always attractive even though it's a very, very small force, if you have much mass, it will get stronger and stronger. There's nothing, as far as we know, that can stop gravity from interacting. So if you have mass, there's gravity. Nothing, you cannot work around that. And that it's an important ingredient that it basically has an unlimited range. So it will, you feel the effect even in the tiniest distance, which all my research is about, so like at nuclear scales, but also at very, very large scales of galaxies and the cosmos. Because there's so much mass present in the universe, it becomes very, very strong. It will be the main force if you look at astronomical objects and astronomical observations you do in the universe. Then the other one is like electromagnetism, and the important thing, it couples to electric charge, so that we have a positive and negative charge, meaning we also can have something neutral where it won't interact. So this is, otherwise it have the same principle, it's an unlimited range as gravity, but it has two opposite sides, so it can either attract or repel. This is a major difference to the gravity. When we come to the strong force, we have, instead of positive and negative charge, we have what we call color. We have red, green and blue, which we think are our charges of our particles. So we think that our quarks we have a red, blue and green, and they should not be confused with the actual color. We're not saying they are green or they are red, they are blue. This is a concept of charge again, as plus and minuses, but all we see in the universe is basically white. So we have to add something which is red, green and blue to make it white. And this is the concept of charge in terms of the strong force. Because it couples to itself, which I will explain a bit later, it is very short range, so it only is relevant on the scale of, say, 10 to 15, 10 to 50 meters, so the scale of the nuclear interaction. And this is why we don't feel the effect right away, but it will come back to it, why it still has an impact on us. Then there's the weak interaction, which also is a very short range interaction, and the important difference to the previous interaction is that we don't have any bound states, that this is only, so to speak, destroying a neutron into a proton. And this is something that we need, otherwise many processes which are essential to life would not be possible. So let's just talk about the strength. So if we go to a small distance of 10 to minus 15 meters, which is the relevant scale for all the nuclear forces, then we can consider the strong force to be of strength 1. If you now compare the electromagnetic forces, 1/100th of that. So it's significantly weaker at that scale, where the weak force is roughly of a 10 to a millionth. So like significantly smaller, and gravity is ridiculously small on that scale, meaning it's, for most of our interest, if you look at the interaction, we can neglect gravity because it's too small on that scale. It only becomes really relevant if you have very, very large distances or if you have very, very massive objects. Of course, this is also what physicists see, is like if you have black holes, then this is something a very tiny object, but a very heavy object. In this object, basically, gravity would be very important because, as I mentioned, gravity increases with mass itself. So the question is, how do we study these forces, and the principles which have been guiding us for the last centuries is like, okay, we have particle collisions, so we take small probes we understand, smash them together and see what comes out. And then there's a very big facility, which the pictures are taken from, which is the LHC facility in Switzerland at CERN. There is the big ring where you accelerate particles to almost the speed of light and then collide them in very big collisions, and then you try to measure and reconstruct what happened inside these collisions. So if you think about it, what we're actually trying to do is like if you make the energy to cars, like if you have an unlimited source of cars, if you want to see what's inside a car and you can't actually look inside, we would just crush 2 cars and we'll see what comes out. If there's an engine coming out, okay, we know engine must be an essential part of a car. And what we hope to see in our experience is also like that we have crashed 2 cars and that a van comes out. And like, okay, the van has a similar building blocks as a car, so well we can understand how things are made up. Of course, this happens very rarely, but if you have billions and billions of cars to smash, nobody get hurt and everything, then this will happen eventually. But this is the whole idea behind this particle accelerator. And if my experiment,
don't do it at home.
Yes, don't do it at home. Good advice. Otherwise, your insurance will kill me for having said that. My experimental colleagues have done this game for quite a while, and now this is basically what we call the standard model of particle physics. So in a short way, this is the periodic table for physicists. So this is all the building blocks we have, and as far as we understand right now. So all of us in the room is basically made out of up quarks, down quarks, and electrons. The rest is just, for some reason, three copies of similar patterns, which is something not completely understood, but we have observed them. We also are pretty sure there is exactly 3, there is not 4, but this is some things we have to understand in the future. There's 6 quarks in total. There's 3 up-type quarks, up, charm, and top. They all have different masses and different charges, but I don't want to go into details too much. Then we have 3 different down-types quarks, which, of course, here the lightest one, then they get heavier and heavier. And then we have leptons, which basically are just copies of our electrons, which exactly is here one of the examples. And there's a copy like muon and tau neutrino, tau, and also its parts of neutrinos, which we need to understand fully the weak action. Then the red ones are what we call gauge bosons. These are basically the particles that mediate the forces themselves. So basically, we think that the electromagnetic interaction is basically governed by the photon. So whenever 2 electrocharged particles interact, they exchange a photon. The same is true if you want to look at the strong force. We have a gluon, which basically glues 3 different quarks together inside a nucleus, inside a proton or a neutron. And then we have the Z and the W boson, which is basically a manifestation of the weak force. And most recently, we added another type of matter to it, which is the Higgs boson. And the Higgs boson is basically couples to everything, not everything, but it comes to most things because it gives the particle its mass. And this is basically how this up quark comes to its mass in our theory. So if we look down to the strong force, here's a small cartoon basically showing how these interact. So the Higgs is the most recent, couples to most of them. There's a line to everything, except for the massless particles, because, well, if it doesn't have a mass, there's no coupling to the Higgs. Meaning like the photon and the gluons are the ones that don't have a mass, so basically there's no coupling to them. But otherwise it's coupled to everyone else. Then we have, again, our force carriers, where we have the strong force, the weak force, as well as the electromagnetic force. And since gravity is so small, in the standard model it's not taken into consideration. So there is no gravitino yet, but this has to be discovered and still is looked for. Then there's the constitution of matter, which, having mentioned this, the quarks, as well as the electron and the neutrino partners. And you can see basically the gluons only couple to the quarks. So meaning the strong reaction only couples to the color of the strong force. This is shown here. While it's the photon, which couples to charge, couples to everything that's charged, like an electron, like the quarks, like the W, but it doesn't couple to neutrinos, it doesn't couple to the Z, it doesn't couple to the Higgs. And all basically is the interaction. There's a few side remarks, it's like the Higgs is massive itself, so it couples to itself. While this is also true for 2 other specimens, it's like the W boson, there's a gluon. The gluon also has colored charge, so charge under the strong force, so it couples to itself. So meaning this will, in the end, will explain why the theory is quite complicated. The same is true for the W boson. It is a charged particle, so by the weak interaction it also couples to itself in the weak charge. And if you go back to the periodic table, all I'm interested in is basically in the following part is interesting in strong force, and we call it quantum chromodynamics because it interacts something with, as the second word indicates, basically it's something with color. So a quantum theory of color interaction, if you want to say so. Everything that has color is basically highlighted here in color, meaning like up, down, charm, strange, bottom, and top, as well as the gluon itself. And this is all the things that interact strongly. So why is the strong force interesting? Well, say decades ago, people believed that the proton is basically made out of only 3 quarks. But quite a lot of studies, quite a lot of theory work has led us to now to understanding that it's much more complicated. In a proton, we have the 3 quarks, which are still inside here, but we also have out of the vacuum popping up another pairs of quarks which disappear milliseconds or nanoseconds later. The same is true, then we have another gluons which also appear and disappear all at the same time. So it's a highly fluctuating, highly complex object we are trying to interested in. So if you consider like well, a proton roughly weighs 1 GeV, and the quarks that make up the proton is like, if you sum them up, rounding about 10 MeV. So we're missing mass of the order of 99% of the proton. And 99% of the protons of its mass is basically coming from QCD interaction, or the strong interaction, meaning like, okay, quarks that appear for a short time, gluons that couple to itself, and gluons that loop around and doing that kind. So 99% of all the mass of a proton and of us basically is given by the strong interaction. So if you go on the scale, you realize you got weight after Christmas, like 99% is due to the strong interaction. Because the theory itself is a rather simple theory. You can write it in a compactified one-line notation. However, it's almost impossible to solve it directly. And this is why we have to rely heavily on computer simulations and use high-performance computing to get a handle on this simple equation. And this is still the source of many unknowns, and also if you consider like what our experimental colleagues measure, most of their uncertainties are actually coming from the strong interaction, if there are strong interactions relevant. So the question we'll discuss in the remaining time is like, how do we solve the strong force? How do we deal with that? And as it's already indicated in the picture, it's like we put it on a computer and solve it brute force. So we, it's not directly brute force, but the idea is like to use high performance computing in order to get some information of the strong interaction. And this is what our approach is basically combining, is basically the theory of the strong force with high performance computing. And the idea is like to put it on a computer and simulate it directly. How do we do that? Basically, you can write every simulation, if you want to have masses or you compute the mass of a proton, you can consider it as an integration over all possible ways. So if you have a starting point and an end point, and we formulate our theory, we can consider that as it would go through every thinkable path, and each path has a certain weight, how likely is that this path has been gone, and there's even like going here and going to the moon and coming back. That is a legitimate path. It has to be considered in our so-called path integral. This is basically just a mathematical way to say we take this expectation value from a start point to an end point over all the possible ways. This is mathematically not well defined. You can write it down, but if it actually exists is a different story, and typically there's no direct statement of that. So what we do, we actually discretize space-time by a hypercubic set of points. So like we think that our universe is basically made out of a finite number of points, which we call lattice. So we have a finite set of points here, very small, and we consider basically that our quarks live on the lattice sides, while the gluons, so the interaction particles, they mediate quarks from one quark to another. And these basically is a mathematical trick to make this path integral in just an ordinary high-dimensional integral. So just a normal integral everyone can solve by hand. And you can show that actually in the limit, if you set the lattice spacing, so the distance between 2 points going to take it away, then this recovers the correct theory. This is an important ingredient, so we have in principle this way to deal with our problem, and then we can remove our systematic error we introduced by putting it on a finite set of lattice points. Of course, if you do that, then it's very famous results. It's like if you have a few input parameters which have to set the quark mass in our simulations as well as the coupling of the simulations. If you do that by the 3 blue points, then everything else is a prediction. So everything else should come out right. And this is what this plot is showing. This is a recent, not that recent, but it's a computation using the lattice approach and comparing experimental findings and seeing if they match. And they match to very, very good precision. And this is a very good indication that we actually studied the right theory, because otherwise it would come out completely different. And also, if you combine it with the including electromagnetism, and this is basically abbreviated by QED, you can find additional very good agreement. And this is which has been obtained only like 3 years ago. This is what you call state-of-the-art simulation for now. So, as I mentioned, this is our approach, and we have just to solve integrals. But the question is, how many integrals do we have to? So, like, take a normal example, like we have 32 points in each space and time dimension. So we have 32 cubed times 8 degrees of freedom, which are coming from our theory, as well as we have 4 directions we can move into. Then we have only, in quotation, to solve 33,500,000 integrals. This is a clear problem for a high-performance computer, for a supercomputer, because like we have here an abacus machine. But going a bit more details, like if we do it in a naive way, so like we do it in a classical approximation, like we would take 4 points in each dimension, then this would be 4 to the 33 million, and this would be a 20 million digit number. Even on a supercomputer, that is impossible to do. So we have to be more clever, and the idea comes back to playing in a casino, so on random numbers. So just rolling dice, letting the computer roll many, many dice at the same time. The important technique here is basically it's based on the Monte Carlo technique, so just random numbers. And the interesting thing is like our integration error, so we do integration over a high dimension integral, scales only by the number of dice rolls we do. So basically this is something independent of the dimension of the problem. So even if it's 33 million integrals to solve, well, if we draw enough random numbers, our error will shrink. And this is basically the whole idea behind it. And to illustrate that, I make a small illustration of the Monte Carlo integration of pi, and just think about a quarter of a circle inside a rectangular, and you just draw a random number, actually 2 random numbers, which is the coordinate of the point, and see if it lies inside the green circle or outside. And then pi is roughly 4 times the numbers inside the circles divided by all the numbers we put in. So here we have 5 points, so 20 over 6, it's roughly 3 point something, so it's a very rude approximation of pi, but you can do better. So if you use, again, our circle here, and the blue points are basically inside the circle, but the red points are outside, and here I used 8,000 points, and pi comes out to be 1.6, which is still far away, but it will get better. Actually, it gets worse. But this is random numbers that can happen. So, but it has to get better in the long run. So meaning like if you take the numbers to infinity. So like let's do that a few more times, and like if it's 250,000, we have 3.14 already, which is better than 1.6, which was quite a way. But it's still converging rather slowly, because 250,000 points is already quite a few. As you can see, if you draw that as a diagram, it's almost completely full. But the problem with that is basically that Monte Carlo integration, if you do just naively is not very efficient, which is due like, okay, if you consider like a function that has a certain probability, then you draw them random numbers randomly, which, well, we know better. We could focus on the thing where the configuration is more important, where basically the probability is much bigger. So basically we would now, the idea to improve that is basically to draw random numbers that are distributed as this probability as well. So ideally, if you know the probability, you distribute them exactly, and then you just cancel out the probabilities all together, and the thing becomes very efficient. And this goes under the name of important sampling. And this is a very important technique we'll use in our simulation. So in the last couple of minutes, I will talk about what my research is about, and I will study a phase diagram of the strong force. This is what I'm after. So, but what is a phase diagram? The phase diagram, very familiar, is basically the one of water, which most people know. It's like at normal pressure, water freezes at 0 degrees and boils at 100 degrees. Of course, this changes as a function of the pressure. And there are certain lines here where we distinguish between basically a gas, a solid, and a liquid. And there's also special points like the triple point, where basically all three phases coincide. And this happens. So the idea of a phase diagram is like to map out these lines and to understand if there's any special points in this diagram. And of course, that's not all the actual theory about water. Water is much more complicated because there's a few more special phases, but I'm not an expert on water. But it's only to illustrate that actually there's more behind it than you would think. There's very different types of solid ice, which are here indicated by different Roman numerals, and also like between the gas, liquid, and the solid ice phase. So what do we know about the strong interaction? So the strong interaction, now we have again a phase diagram, which is basically a function of temperature, this time on the horizontal, on the vertical axis, and the density, which goes into the same as pressure, on the vertical axis. And we know we currently live in where everything is basically a gas of hadrons. So we live in this phase. My experimental colleagues, if they smash atoms, and also we know in the early universe that the universe has been in a state which is called the quark-gluon plasma state. So basically where it's that hot and that dense, so hot and dense, where basically quarks and gluon could behave freely as in any plasma. And this is then, we know that a phase like this must exist. So there must be a line separating these two, but if you be honest, like this is the state we know that. However, basically, we have a few more understanding from model calculations what we would expect. So there's again supposed to be a critical point. There's other different states of matter. And there's even new states of matter which have been not found and have only been predicted. And that would be like if you have ice, liquid, and gas, then also a plasma, and also like you could have colored superconductors, something that has normal superconductors, but only like with a colored charge of the strong force.
I mean, sorry.
Yes.
When you say, an infinite, so there are limits, so you can prove rigorously that,
they should exist in the limits.
This exists.
Yes.
Then whether, this is applicable to energy range where, it's applicable to neutron stars, this
Sure.
is another story. But you can prove it mathematically.
Yes. Well, we know basically that this is also why we believe it is there, because if you go to infinitely high density, whatever that means, such a state should exist. But if it's any relevant for daily life, in quotation, that is something to be seen. If it ends here, or if it ends like at densities that are the Planck scales or not relevant for our current investigations. There's a bit more cartoonic version of it, which is typically also indicating a few more things. It's like, why is it interesting in the first place to understand the QCD, the phase diagram of the strong force? It's like we know the early universe, so basically when the universe started, it was in a very hot and very dense state, because it was very small, because it's constantly expanding and expanding. And by expanding, it cools down effectively. So meaning it must have gone from a very hot and very, very dense state to the state we live in right now. So this is something to be understood for astronomical observation, this transition from very hot temperatures to very low temperatures. As well as there is already indicated, as Francesco also mentioned, neutron stars are relevant in density areas where people believe that this transition occurs. And so this is something, we know that neutron stars must exist, but we don't know how they be built inside and how the matter is really interacting here. Last but not least, there is two arrows here indicating current and future facilities, like big collision experiments that will try to map out this diagram. Okay. As you remember, I've shown the diagram previously, and it's basically blind, so it's a shot in the blind. So my work as a theorist is basically to try to have an idea when it happens, where it happens, so my experimental colleagues know where to look for them, or how to look for them, because we can also give them an explanation how quark-gluon plasma phase should behave in certain respects. So the problem we're facing at the moment is like what's known as the sign problem. As you probably have seen, the probability we used before for the Monte Carlo integration, so we have a nicely shaved fine where we basically can focus on the region where the probability is the highest, and then basically take our random numbers from there. But unfortunately, if you study the finite density, as we need to for the phase diagram of the strong interaction, we obtain a sign problem, meaning like, okay, this nice behaving probability distribution becomes actually something like a complex value, so it oscillates wildly, and now it's very hard to determine which are the states, so how should we choose our random numbers in order to get the highest value of the peak, because well, the exact calculation relies on the fact that we know can precisely cancel these effects close to each other. And this goes under the name of the sign problem, and then all the importance sampling method failed. So my research is basically using what is called as complex measurement simulation, which is based on a completely different approach. And instead of sampling the path using random numbers to describe them, we go back to a stochastic process, like a Brownian motion of everything in a gas, like where we have random and like let it fluctuate randomly, and this way pick up all the relevant degrees of freedom in our integration. This is going by the name of complex measurement, and the complex indicates that basically, in order to work, we complexify degrees of freedom. So we go from real values to complex values. So we can have, without the complexification, we can avoid the sign problem in a very elegant way, but it also has a few downsides, which means this is a complete new approach, and it has to be understood, because there's certain limits in which we know it works, and in certain limits we know it will not work. So the question is if the things we're actually interested fall into either of the categories, ideally to the category that we can simulate it. And there has been studies like of complex measurement. The process is like you do random process, and then like you randomly go through the different values, and then you obtain a nice expectation value for, in this case, a plaquette, which doesn't have to mean anything for you, but we can observe, we can, again, even if we have a sign problem, measure values and get uncertainty assigned to it in the same way. The idea is basically now, okay, we have our T mu plane, so the temperature and density plane, in order to map the phase diagram of QC of the strong force. And it's like, okay, we don't know either where to look for, but on a computer it's easy. We can just tune a knob to make the temperature different, we tune a knob to make the density different. So we can effectively build a grid of points, which allows us to, well, ideally include the transitions and try to find where they happen and how they happen. And this is now basically done on a toy model. Basically we take the strong force, but we make the quarks heavier than we can, because this way computer simulations will become cheaper and easier to do. And this goes under the name of heavy dense QCD. And it serves as a purpose to test that our method is working and that we can actually get results out. And this is what I will show in the last few slides, is that we actually can. And this is basically the three-dimensional plot of the phase diagram now as a function of the temperature here in MeV units, as well as the chemical potential in an arbitrary scale. And each of the black points of the on this three-dimensional chart is basically the result of a single simulation. And so you can see, like, we have done quite a few, but we successfully can map out some features of the phase diagram. Because in one phase, in the hadronic phase, basically the value is expected to be 0 or purple in this by the indication, while everywhere where basically it's not the hadronic phase, we should see a value that is non-zero or indicated by every other color than purple. And you can see, like, okay, you see a line arising where basically when it goes from 0 to non-zero value. And this is exactly how we can map out the line here in between. And this is what the next plot shows, is basically, again, temperature versus density. And this is what we have found as the current borders of the heavy dense approximation of QCD. And this is a first principle calculation of its kind. Of course, the next step would be to go to lighter quarks. So we actually study the scenario which we see in nature. But this is still ongoing. But there's results to come soon. Yes?
Is this first order or?
This is believed to be first order, yes. But this is known to be first order because...
Yeah, it's larger than large quark limit.
Yes, exactly.
So there is no end of the first order?
There's no endpoint to be expected, unfortunately, because
yeah.
in the limit of heavy quarks, the theory comes that simple, or that dull, if you want to say that basically it's only going either to this state or that state. There's no intermediate state to be formed. So the phase diagram will be looking very empty, so it only hadronic phase and the non-hadronic phase.
But this is more like the width and cosmic separation of phases, where basically you have the kind of this.
Yeah, you can say that.
So you have actually truly confinement phase transition because you have pure Young Mills.
Effectively goes into pure Young Mills in that limit.
So first order then, all the way until.
Yes, exactly. And so I hope I convinced you that the strong force is quite an interesting force, has quite a few problems to solve for. For the sign problem, the thing that heavy oscillation is one major problem. But I hope that basically our method of complex measurement might be a solution, but this has to be seen. And there has to be a lot of work to be done. With that, I would like to thank you for your attention.
Yes, thank you, Ben. Very nice. Any questions? Yes, please.
So this method is basically complexifying the integral, and also the Picard-Lefschetz method is also doing that.
Yes.
Can you comment on, like, the difference of this method and the Picard-Lefschetz and the difference in the performances?
Yes. Well, I know it's a Lefschetz stimulus, but it's the same theory. These are they are related to another, but one has a direction. If you write down the trajectories you have in the Lefschetz stimulus, these are orthogonal to the complex measurement action. Meaning, like, the Lefschetz stimulus always approach the highest value of an action in a complexified way of the action. While the complex measurement is a stochastic process, so this one has an additional stochastic kick inside the forces, which covers around to kicks the forces around in the bigger complexified manifold. You can show that complex measurement has problems with convergence, which Lefschetz stimulus have not. But Lefschetz stimulus can, because you have to identify all the thimbles in principle, you can trade a sign problem for an overlap problem. This has to be shown. For the complex measurement on the convergence, there is certain criteria found. If they are met, then you know that it converges to the correct result. But if they're not met, then you do not know. So this is actually an active field of research, because it's important to know the certain limitations. For now, we know that the heavy dense limit of QCD, certainly the criterions are met and it's all fine, so we can study it. So the question is, if you lower the quarks now, if it still holds or if it doesn't. This is still ongoing, and unfortunately on the convergence I cannot say anything yet. On the left thimbles, they have demonstrated that it works in certain regimes, but they have nowadays basically do something which is known as well, you milden the sign problem a bit in order that basically you combine it with a flow equation as well. Like Langevin is a flow equation, and if you flow into the complexified space, the sign problem becomes milder. But the different thimbles, they still have a gap in between, and the question is if you can overcome the gap in between, so if you still have an overlap problem or not, is to be seen for that method. But both methods are quite promising, and I wouldn't say one is better than the other, but I think both are needed because we have a phase diagram to explore where we basically, if I would be complex modular, predict you one phase diagram, well, we have to check it somehow. And so another method that is on solid footing is absolutely necessary because, well, we can't simulate directly. I hope that answers.
Good. Yes.
I have a question which
Sure.
might just display my ignorance. But I'm just wondering, when you say it's a solution to quantum chromodynamics, I mean, I saw you had a formula
Yes.
on a previous slide.
Well,
and that was the reason why you're using these path integrals. But what does it mean to solve it?
well, we have a.
You say
I say like
solve
solving it in a
quantum
numerical fashion. So I have a numerical tool that allows
What does
me
it
to.
mean? I mean, what do these numbers signify that you compute compared to the formula that you started with?
Well, they correspond to like, well, we take the formula, which is just if you integrate over the space and time, it's just an action. So this gives us a weight of our configurations. Now in the phase diagram, we basically have a complex weight, but we still can get so-to-called expectation values of the QCD action with respect to what you, well, everything can be, well, every mass and everything is an expectation value of the theory. So
it's
what we're
kind of
trying to
number
solve is like
system.
we get out expectation values of a theory. So we ask it specific questions like, okay, what would the mass of a proton be in this theory? What would be the tension of two quarks being if we pull them apart? And then, well, we sample it numerically and then we get an answer to an expectation value.
But
Yep.
it's really this kind of path integral that you want to compute. Or
Yes.
What is it?
Ideally, yes. Ideally, we want to do the path integral.
And how do you know that what you're doing is converging to what you're actually looking for?
Well, if you do the lattice approach, basically it's just an ordinary integration, high-dimensional integration, which by definition is convergent. If you take the limit of the continuum limit, so basically removing the lattice again, removing the lattice spacing again, and removing also, like we have a finite box, we make the box bigger, understand that?
But do you know how fast it converges? Say,
Yes, we do know the convergence,
Okay,
because
okay.
this is important, otherwise we would be in the blind.
Yeah, sure. I mean, you could do very.
And you can make the
Large
convergence
lattices, but-
quite fast if you want to. So
Okay.
if you choose your actions, because you have some, because of the lattice approach, you have some choice, some wiggling room, how you make your action to be approaching the continuum, you can make it quicker or slower, the convergence. But we know it's typically converging at least quadratic on most of our simulations. So if you,
I think we had another
Sorry.
question.
Yeah, and actually, first I comment on your question and then a question.
sure.
The comment on that is that you can solve exactly some quantum field theories, right? Example, we can have solved n equal to 2 exactly. So what does it mean solving a theory? It's technically calculating all the Green function in your theory for gauge singlet operators. So once you've done that, the theory is solved. Yeah.
Okay.
That's actually a hands-on demonstration to solve the theory. If you do, for example, differential equations and you find basically the spectrum of operators, you solve the theory. So that is a definition.
So you're looking for the spectrum.
Yeah, so the spectrum is actually a solution of the
No,
theory.
okay.
So you can spectrum by all other physical property of the theory. So
And
like-
the eigenfunctions.
Exactly. And so in certain cases you can solve the theory. You could also check, for example, when you say you have another method to prove you're correct, is if you go at high density where I can demonstrate the theory, and you do your calculation at high density, and you demonstrate that actually correspond to current superconductivity, you solve the theory on your so standard. So we have actually a number of theorems guaranteeing that actually there are things with which we can take infinite value limit, the lattice spacing equal to 0, and you can mathematically prove the consistency of your theory. So this actually, I mean, there isn't even a problem by that. There are other theories which are empirical theories for which you have other instances you have to consider. But in this case, you can just solve the theory. Now, there's a numerical solution and there's an analytic solution. So, as you know, there is still the Miller Prize for proving confinement. Confinement has been proved numerically, it's not been proved analytically. So you can still get $1 million and should be fast enough, it doesn't get. If you prove analytically the existence of a mass gap computing immense theory, which has been proved by lattice simulations, but not analytically. And that, as a mathematician, you can still do that. But actually, a more technical question for you. I mean,
Sure.
Assume that you're successful, right? How long is it going to take? I mean, to actually prove this with you, right? Because I'm interested, because this is interesting for actual astrophysical issues, right?
I would relate your questions and give you a very definite answer like it depends.
Yeah. Yeah, but I'm not interested in politics. I'm interested in actual facts.
No, I mean, like, okay. Currently, we are in the process of basically going from heavier quarks to lighter quarks. This is basically, well, it worked fine with a few problems on the road. So, like, this is something, well, we expected because the numerical inversion becomes harder and harder, which is something we know. So, this is basically limiting us to go to lower temperatures at the moment. Otherwise, to map out the full phase diagram, to have the order of the phase, you need a volume study, you need everything. This means you have to have lots of simulations at lots of different parameters, and I think the earliest results I would hope to have in 3 to 5 years, but this would be, I consider them very preliminary. That's why I said it depends. If you want to have robust numbers that have been tested with various different approaches, this will probably take a decade. I'm confident about that, but that's why I think, depending on the level, if you're happy with some preliminary results, seeing some first indications about the lines, that's probably we can do in 3 to 5 years.
Compared to other groups worldwide, I mean, can you get there first? I'm sorry, this is really biased, so I'm allowed to be a pain. So.
No, that's a legitimate question. Well, I think on the footing of complex algebra, I think we probably one of the world's best. So we would be the first to, if that method is successful, we would probably be the first here. However, if there's other methods being found in the meantime that do it quicker and better, well, they beat us to it. That can happen. But on the complex algebra, I think we have a solid standing here.
Are there any other questions? So less technical questions.